Okay, so I guess we can get started now. This is sad, isn't it? If you call it sad, this is the last lecture. That means last homework is due today? Okay, any discussion before we get started? Questions about anything? Okay, so we're going to just, yes?
Just a small question. How is this phase matching mirrors, phase conjugate mirrors?
Yes.
How are they in reality in the lab? Are they just a surface or are they a crystal? How are they in reality?
So the ones I have built myself have been in a sodium vapor. It's a Chi3 material. Atomic vapors have very large Chi3 values. So it sort of depends on whether you're having fun or whether you're doing something useful. If you want to see these effects and study them, sodium vapor or rubidium vapor is a very nice way to do it. You can ask the question of whether you can imagine any real-world device operating on a sodium vapor. Well, street lamps, even today, street lamps have sodium vapors in them. So you say, well, maybe, but gee, solid-state devices are a lot nicer. Some of the early work was in liquids. Carbon disulfide has a large nonlinear response. So that's one level of answering your question. People today who are using phase conjugate mirrors for real applications tend to be using stimulated Brillouin scattering as the process leading rise to phase conjugation. We didn't treat that this year. So why did we do what we did? Because the degenerate four-wave mixing in a very clean way leads to phase conjugation. For the case of stimulated Brillouin scattering, it does not seem as if it would work. It's only in a statistical sense that stimulated Brillouin scattering does lead to phase conjugation. So the conceptual points were much better expressed in terms of the degenerate four-wave mixing, even though that's not probably what you would do if you were trying to implement this in a realistic scenario. But great question, thank you. Okay, last lecture we were talking about Fermi's golden rule. And how far did we get? I will write down an equation, which I think was the last one. And if it wasn't, then you can correct me. But I'm sure, I think it's likely enough that I have this right, that I'm not too scared about this. Or am I? Who has their lectures from last time? IH bar? Yeah, okay, yeah. The way I knew is because my notes are open to that same page. Okay, so this is a derivation of Fermi's golden rule. It's sometimes called Fermi's golden rule number 2. Fermi, a good Catholic, acknowledged that Fermi's golden rule, that the golden rule is do unto others as you would have them do unto you. So he says that this is only golden rule number 2, not golden rule number 1. Okay, so here's where we got in the derivation. We got to the point that IH bar dAm dt, so this is an M, is sum over L ALT VL of, what am I doing? VML e to the minus I omega LMT, where omega LM is EL minus EM over H bar, and VML is the integral of UM star of R, V operator UL of R D3R. Okay, so this is, I believe, where the last lecture ended. So a nice compact form, but nonetheless, usually you can't even solve this one here. So we find an approximation scheme in which to do this. So we will solve using perturbation theory. Which we've been through at least twice already this semester. But the details are just a little bit different because we're solving a different problem under different initial conditions. Okay, so we take V ML and replace it by lambda V ML, and we look for a solution of the form A M of T is equal to A M0 of T plus lambda A M1 of T plus lambda squared AM2 of T, etc. So this is the first order correction. This is the second order correction. And now, in terms of the orders, well, there's a 1 here, that means it's the first order. There's a 2 here, that means it's the second order. But perhaps more physically, if lambda appears twice here, that means that the interaction, V, occurred twice. So that's really what you mean. This is first order in the interaction strength. This is second order in the interaction strength, etc. So we take this equation, introduce it into this equation, then we equate equal powers of lambda, and we get the following equation: A M N d by dt of AMN is IH bar to the minus 1 sum over L AL n minus 1 V ML e to the minus I omega LMT, and this is for n equals 1, 2, 3, ... And if it seems like I'm going quickly, I am, because you've seen it many times before. I'm very proud of this. It's my Christmas tie. My other one has Santa Claus on it, but that didn't seem dignified enough for being video recorded. But you'll see the Santa Claus tie before the year is over. Okay, so And as we pointed out before, you solve these in order. If you solve the 0th order first, solve first for, if you know n minus 1, you can calculate n. Then you put that here, you can do n plus 1, et cetera, et cetera. So there is no limit to how far you can push this technique very, very straightforwardly, assuming that the series converges, which is something we would want to take a look at eventually. Please protect me from myself. Don't let me erase this. So let's first of all look at the linear response. And of course, what are we doing? We're doing multi-photon absorption, so the linear response would correspond to 1 photon absorption, which is to say the process in which an atom goes from the ground state, I just want to make sure I have the notation right, to some excited state L by the absorption of a photon of energy h bar omega. Okay, so that's the process we're treating, which you know how to do already. But once you see how to do this one, then immediately you can generalize it to higher orders. We have to specify the nature of the interaction. So let's take Vmg equal to minus mu mg e to the minus I omega t plus, I'll write it out, e star e to the plus I omega t. Something like this. Now introduce this into here. And what do we find? But that dAm1 dt is equal to minus IH bar to the minus 1 mu mg e, let me write this way, e to the I omega mg minus omega t plus e star e to the I omega mg plus omega t, and we'll put our parentheses there. We are so happy now, right? The right-hand side is a known, very, very simple function of time. So you can just integrate this equation, and you find that AM1 of t is minus IH bar to the minus 1 times mu mg integral 0 to t, right? We're doing multi-photon absorption. You start the integration at time equals 0. You assume that the atom is in the ground state initially. You want to determine the rate at which it makes upward transitions. Integral 0 to t dt prime of e to the I omega mg minus omega t prime plus e star e to the I omega mg plus omega t prime. And this is an elementary integral. So the first term is mu mg e over h bar omega mg minus omega times e to the I omega mg minus omega t minus 1, the 1 from the initial condition, of course. And the second term is mu mg e star over h bar omega mg plus omega e to the I omega mg plus omega t minus 1. Now, let's look at these two terms. Now, I guess I've changed letters of the alphabet. This is M. So this term here can become resonant. All you have to do is tune omega to this transition frequency. In fact, it can become embarrassingly resonant. When you get a 0 in that denominator, we're going to have to worry about that in a few minutes. But clearly this can become resonant. This cannot become resonant. So we just drop this term here. So this term is so much larger than the other term that we drop the first one. Now, we want to know what's the probability that we are in level M. At time t. We can call that P1 M of t. Probability to be in level M to first order in perturbation theory at time t is equal to A M1 of t modulus squared. The squared modulus of a probability amplitude is always a probability. So this then becomes mu mg e over h bar, squared times e to the I omega mg minus omega times t minus 1 over omega mg minus omega modulus squared. You've seen this before, right? So it's the same integral we had in the phase matching function. Here we have time, that was a z integral. So we can just simply rewrite this. How did the board get clean all of a sudden? It heard me complaining about it, I guess. Oh! Thank you. Half of it's there. I'll put it back later. No, I have. In fact, you can even see it. In fact, let me put it back now. D A M N D T is equal to I This time I'll draw a double box around it, make it even less likely that I will forget myself and erase. So let's just continue then. P M1 of T. So same mathematics as before. mu mge squared over h bar squared times 4 sine squared omega mg minus omega t over 2 over omega mg minus omega squared. And this quantity here, 4 sine squared, this over this, let's call this f of t. And let's take a look at how f of t, let's take a look at the functional form of f of t. And this is the one that we said we're going to have to play a few tricks on ourselves. Fooling yourself is never a good idea. Right? Obviously, this is divergent, but we're going to fool ourselves into thinking it isn't. And I guess this was Fermi's contribution, was to find one way to circumvent this problem here. So, actually, let's write this as t squared sine squared x over x squared, where we have defined x to be omega mg minus omega times t over 2. Okay, so dimensionless quantity, but overall a times squared dependence. Now let's plot f of t as a function of x, and we get a curve. Oh, it's a sinc squared curve, so it's going to look something like this. But this peak value is going to be equal to t squared, because the evaluated at x equals 0, sine squared x over x squared is equal to 1. So let's see, 0, pi, 2 pi, etc. So you have a curve here whose full width at half maximum is approximately 2 pi over t, because x we said is omega mg minus omega times t over 2. So in real units, the width of this is like pi, but in terms of frequency units, the width of this is 2 pi over t. Now, you look back into your memory banks. Have you ever heard of a function that whose peak increases without limit and gets narrower at the same time? You say, hey, yeah, this is a delta function. So this is one of the standard ways of representing a delta function. So this was sort of Fermi's recognition here. And I'll look at my notes so I get the factor of 2 pi's in the right place. And let me get some more space here. So in fact, the limit as t goes to infinity of f of t is 2 pi t times delta of omega mg minus omega, which allows us then to write this probability in a still unphysical form of 2 pi mu mg e squared over h bar squared times t times delta of mg minus omega. So this cannot be the whole story. It says that the probability is either 0 or infinity, and the probability can't be even bigger than 1. So this is a step along the way. Now you ask yourself, what was it about the calculation that we did? I mean, Schrodinger's equation was not wrong. I mean, I don't think we made a mathematical mistake. So what was it in this calculation that gave rise to this unphysical answer? And it was that we assumed that this is infinitely sharp. Of course, if this were not infinitely sharp, then you would never have an exact 0 in the denominator. So Fermi says, let's assume that this upper level is spread out into what he called the density of final states. And we can call this rho f of omega mg. This is g, this is m. So here the density would be a delta function. Here the final state is spread out into a continuum. Let me define it more carefully. Rho f of omega mg d omega mg is the probability that the transition frequency lies between omega mg and omega mg plus d omega mg. And my apologies for writing it out in words, but historically one knows this is a very confusing point. No, you hear the lecture, you go home, you think you understand it perfectly, you get home, and then you cannot reproduce the argument. So, you know, I know because the first half a dozen times I taught this, by the time I got home, I'd forgotten it already. And we normalize. Well, it is normalized. If it's a density of final states, it has to be normalized such that the integral from 0 to infinity, rho f of omega mg d omega mg is equal to 1. So there's some probability distribution. There's certainly a transition there. It's just that the exact frequency is not precisely defined. So there are many examples you could give. And in fact, you had a homework assignment, or did we this semester? I said for a whole bunch of line-shaped functions, determine the refractive index distribution. Okay, so so you know that there are many, many line-shaped functions. When you're talking quantum mechanics, you call it the density of final states. In optics and photonics, it's just the line-shape function. Because that's what gives rise to the line shape, is the fact that the upper level is spread into a continuum. So as you know from your homework assignment, there are several different canonical forms for a line-shape function. There's the Gaussian, there's the Lorentzian, which is named after the St. Lawrence River, or is it the other way around? But St. Lorenzo, if I recall correctly. I mean, all those saints were Italian. Okay. So let's do the Lorentzian because this is the one. Well, spontaneous emission gives rise to a Lorentzian. So if one of these is more fundamental, it would be that. So the example that we will give here is that of a Lorentzian. Rho f of omega g is 1 over pi gamma over 2 omega bar, for lack of better, mg minus omega mg squared plus gamma squared. My handwritten notes say 1 over gamma squared. I can tell you I have good statistics now. If I write 1 over gamma squared, 1 time in 10 does the class tell me that it's wrong? 9 times out of 10 they will allow something absolutely ridiculous to be there. That's because giving a lecture puts people to sleep. Your brain shuts off. Plus gamma squared. So I've just defined omega ng bar as the mean frequency or as the center frequency. Of course, in the US, I give the lecture entirely differently. C-E-N-T-E-R. Maybe I've told you this already. I know I'll never learn French, but at least I can try to learn Canadian spelling of English. Okay, so the Lorentzian looks, the Lorentzian function then, rho f as a function of omega mg looks something like this. And it is centered at omega mg bar, and it has a width that we could calculate later. It has a width of gamma. Note that it's a function of omega mg, not a function of the laser frequency omega. Okay, so now what do we do? Well, this is the probability to be in the upper level if the transition frequency were omega mg. But we actually have a distribution of transition frequencies. So all that we have to do is average this result over the various possibilities for the transition frequency. This time I leave it. So we find that Pm1 of t is 2 pi mu mg E squared times T over h bar squared, integral from 0 to infinity, rho f of omega mg delta omega mg minus omega d omega mg. And of course, integrating over a delta function just extracts the value of the line shape function at the laser frequency. So this then becomes 2 pi mu mg E squared T over h bar squared times the density of final states. I'll write it this way here. Evaluated at the line shape function calculated at the laser frequency. So I just choose to write it this way. We can now define a transition rate. So we can call this R mg1. I'll use the convention of quantum mechanics that you read right from left, as in some other languages. You're supposed to smile, right? As in some other languages. So you start in level G, you end up in level M. So we will write it in this form here. So the rate is just the probability to be in level M at time t divided by the time t. So this is 2 pi mu mg E squared over h bar squared rho f omega mg equals omega. So this is what people refer to as Fermi's golden rule. It's more general than just the electric dipole transition. So you can write this more generally. Let me just make sure I have my factors of 2 in order. I mean, you can write this as what we called mu mg times e to the minus I omega t. You could just call that vmg e to the minus I omega t. So Fermi did not restrict this just to electric dipole transitions. He says you put the interaction potential here, and this tells you the rate in which the transitions will occur. Okay, so this is Fermi's golden rule. It tells you the transition rate. Now, we conventionally measure rates in terms of a transition cross-section. So we can choose our mg1 to be sigma mg1 of omega times I. Well, this is let's just say it's the intensity in photons per meter squared per second. Okay, I mean, you can have a physical intensity divided by h bar omega, but I think for problems like this, it's better to just think in terms of photon flux. So, you know about cross sections, right? It's the effective area of the atom. A stream of photons comes at it. You ask what fraction of those photons actually hit the atom. So knowing the transition rate now, we can find that sigma mg1 is equal to r mg1 divide, let's call it I sub p for photon. Okay, so that would be it. And I guess we wrote this here. Was anybody paying attention?
Missing it. Yeah.
I'm missing an e squared, right? Oh, good. I'm glad you were quick on the ball. You didn't have to. Okay, so of course this intensity gets rid of the e squared here, and you can work it out whatever units you want, because there's so many conventions. You can do it MKS, you can do it in Gaussian units, you can do it in terms of photon flux. So let's just leave it in that way here, and you can turn it into whichever notation you find best. Okay, so now we want to turn on to 2 photon absorption. So we're going to go to n equals 2. But this will, so let me ask if there's any questions about the 1 photon absorption, because then I want to erase. Yeah, question.
So, obviously it works, but there's no senseless photon here. We're just working with classical.
Oh yeah.
Right.
Right.
Whereas how do we get 1 photon?
Well, okay, this was the result. I said if you want, you can write this in terms of a photon flux. But you don't have to. Okay, so here's the answer. And there are no photons here.
Yeah.
There's no photons here. We, and maybe me worse than other people, get hung up too much about what's quantum and what isn't. I mean, everything is quantum. Right? At times we can sort of look away and pretend that we have a classical theory. But yeah, we did not quantize the electromagnetic field. This result is totally adequate. Well, I challenge you to think of an example where it's not. I think there's a theorem that you have to go to higher order correlations in order to find the difference between classical electromagnetism and quantum electromagnetism. So this is correct. If you want, you're allowed to write it this way. And that's and I meant nothing deeper than that. Good. Thank you. Other discussion? Yes.
So when we define the function f of t,
Yeah.
right afterwards we took the limit as t goes to infinity to define the delta function.
Right.
So this is only valid for t goes
Oh.
Is that right?
Yeah, but I mean, well, it means, you know, it means t much longer than other t longer than other timescales in the problem. And I didn't come to class today with a crisp answer to this. Let's see if I can think of one right now. Did you have a homework problem about Rabi oscillations damping out? You didn't? With the density matrix formalism? Okay, you're lucky. Okay. So it's a homework problem at the end of chapter, the two-level atom. chapter. I think you want the time has to be much larger than T2. You want the coherent response to damp out. I mean, you do have Rabi oscillations, and in fact, our equations here even would I mean, it was a T squared. So if okay, so if you take the equations we derived, well, if you solve them exactly, which you can do for a two-level atom, you get something like this. This here, this little part here is a T squared. Sine squared. Sine squared starts out looking like T squared. And that T squared that we had, we did hand waving to make the T squared go away. But this is, this initial turn on is the beginning of the Rabi oscillations. One of the homeworks showed that these oscillations will die out. For technical reasons, I'll call it P sub m. I mean, A sub m is the probability amplitude of being in the upper level, but after a few collisions have taken place, this is a mixed state, not a pure state. So you just, the thought, I believe that the thought is still correct, but notationally you shouldn't call it this. So you want the Rabi oscillations to die out. That's how long you have to work. That's how long you have to wait in order for this to be valid. Good question. Question is much better than the answer, but that I wasn't planning on that. Many of the textbooks, I go into that in detail. Okay, so let us go on then. So now, let's do this for n equals 2. And I'll just fix it up here. Okay, so we had just calculated the formula in your notes for the probability amplitude, the first order, to be in level L. So now, what is the nature of the calculation? You're in G. You want to make a transition to level M, and there's some level L that is non-resonantly excited. So to first order, you go from G to L. Then from second order, you go from L to M. So that's the calculation that we will be doing right now. But I've actually labeled these a little bit differently in the lecture notes that I'm using now. So this is level M, this is level N. So we want this to be N, and we want this to be M, and we want this to be M. And we want this to be V, N, m. Okay, so now v n m will be minus mu n m e to the minus I omega t plus e star e to the plus I omega t, like so. And now that we understand what's going on, 1 second. Now that we understand what's going on, we will immediately drop the second term and just take this equal to mu n m e to the minus I omega t. Any question?
The capital M, that's number of photon?
Oh,
Number of photon?
no, I'm sorry. This is order of perturbation theory. And I think it's easier just to go back to the equation. Go back to this equation.
Okay.
Yeah. And was just a number that told us what order in perturbation theory we were working. Okay, so then this equation becomes d by dt of a n 2 of t I h bar to the minus 1 sum over m a m 1 of t v n m e to the minus I omega m n t. So now we look back at your notes, find the expression for am1 of t. Which is just a, the time dependence is just an exponential. So the two exponentials multiply together, and we get, well, you can actually just do, I'll write it down with the integration performed, minus IH bar to the minus 1, sum over m, mu n m, mu m g, e squared, h bar omega m g minus omega. Okay. Yes. So all I've done is I've taken a sub m, introduced it here. So we have this left over from before, and now we still have an e to the I omega n g minus 2 omega t minus e to the I omega n m minus omega times t. Now, similarly, so all I did was I substitute in for this quantity here. Now, we have two terms, first term and a second term. This term here describes two-photon absorption. The energy of two photons, twice omega, would make a transition from the ground state to level n. This term here is not two-photon absorption. It's some sort of transient. It does not lead to two-photon absorption, so we will ignore this term. Now, we have just this term here, and again, we can immediately integrate this equation. So we integrate, and we find that a n 2 of t equals sum over m mu n m mu m g e squared h bar squared omega m g minus omega e to the I omega n g minus 2 omega t minus 1 over omega n g minus 2 omega. Okay, so we perform the integration. We perform the integration. What can we see now? It's second order. E appears twice. We're second order in perturbation theory. The matrix elements are linked together. G to level m, m to level n, just the way this diagram here shows it. We have two terms in the denominator, the one-photon resonance and the two-photon resonance. The one-photon resonance we can just leave as it is. This one is not going to blow up. This one here is the one that is going to blow up under conditions of two-photon absorption. So we play the same Fermi's golden rule trick with the second term, but not with the first term. So let's do that. It's it's step by step what we just went through, but let's quickly go through it anyway. So the probability to be in the upper level to second order at time t is a n 2 of t squared, and this will be sum over m mu n m mu m g e squared over h bar squared omega m g minus omega squared times e to the I omega n g minus 2 omega t minus 1 over omega n g minus 2 omega squared. And now we'll play that same trick as before, and we'll say that we can write this as sum over m mu n m mu m g e squared h bar squared omega m g minus omega squared times 2 pi t times a delta function of omega n g minus 2 omega. Does it look familiar? It should, right? line by line. We just went through the same sort of calculation. So the probability to be in level n at time t is itself proportional to t, so we can define a transition rate. Of course, if it didn't scale linearly with t, we couldn't define a rate, at least in the usual sense of the word. We couldn't. So we now define the transition rate in going from level G to level N to second order in perturbation theory as the same thing but without the T, sum over M, mu N M, mu M G E squared H bar squared omega mg minus omega squared. Did I make a mistake? I squared it twice, I think. No, that 2 is not here. And this 2 is also not here then. So this is the transition rate. Two pi rho f omega mg equal 2 omega. And if we want to, we can define this to be the 2-photon cross-section for a transition from the ground state to the excited state times I squared in any chosen units. So I think we can stop this here. Let's see, were there any things?
Why would we have an I squared?
Because, well, first, it goes like e to the 4th. It goes like e to the 4th. It's 2-photon absorption, so you would expect the rate to go like the intensity squared. So this would be the rational way to define a 2-photon cross-section. It's 2-photon cross-section times the square of an intensity gives the rate. So what is a typical value of the 2-photon cross-section? It's 10 to the minus 49 centimeter 4 seconds per photon squared. And does anybody happen to know the definition of a Gerbert-Meyer? Physicists want to immortalize themselves by giving names to things, right? We have Webers per square meter. We don't even know who Weber was, do we? We have Webers per square meter. Maria Gerbert-Meyer was the first person to do this sort of calculation. So the unit of 2-photon cross-section is often called the Gerbert-Meyer. G-O-E-P-P-E-R-T? Or GM? Okay. I mean, which within a factor of 10. A Gerbert-Meyer is this. Okay, so Okay, so we are, well, usually we would go a little bit longer before the first break, except that we're at a stopping point here. So why don't we take well, answer some questions, then we'll take a break. Yes?
So when we talked about optimizing third harmonic generation in some chapter before, there was a comment that says there's no linear absorption for one photon.
Right.
But there's no linear absorption for two photon processes. There's only odd orders.
Right.
So is there some connection between that and the what do you call central symmetry? You don't have second harmonic and odd order permutation orders, things like that. So,
okay, well, a whole bunch of it. Oh, let me just say some interesting things that are related to your question. Okay, as we said a week ago, the two photon cross section sigma 2 is proportional. How do you do proportional? Is proportional to chi3 to the imaginary part of chi3 omega equals omega plus omega minus omega I assume squared. I assume squared. I think last week I forgot the square, but the more I think of it, okay, so that's the first thing, is that you can look at two photon absorption in either of two ways. You can calculate the transition rate. That's what we did here. Or you can say, I don't like rate equations. We are sophisticated people. We want to keep track of the coherence properties of the light and of the response that they induce in the material system. So I will look at this differently. I will say I'm going to treat this parametric process I will ask, how do these three fields develop a polarization that will modify the amplitude of this field here? So if I want to look at it that way, the material develops a nonlinear polarization that modifies the amplitude of this field, then this is how you would do the calculation. So I guess that's the first point, is that there are two ways of looking at this. Yeah, we went through this because then somebody says it's 2n minus 1 or something. Yeah, so I remember that discussion. Second comment is that third harmonic generation I'll define a new symbol. This means is of the same order in perturbation theory as two-photon absorption. So third harmonic generation is of the same order of perturbation theory as two-photon absorption. So, so the treatment of third harmonic generation, you really should include two-photon absorption, because you've ignored something which is of the same order of magnitude as what you treated. But of course, there's a very easy way to avoid two-photon absorption, and that is to make sure that you're very much detuned from resonance. But they're the same order of perturbation theory, but they have very, very different frequency dependence. Did that help? It wasn't really your question, was it?
Well, I wasn't here for this 2n minus 1, but hearing the 2n minus 1, I think
Yeah.
that
Okay.
answers my question.
Okay.
It's 2 and
Yeah.
then
Okay, let's take like a 5-minute break or so. Okay, so next topic. Next topic is optical damage. Maybe not the most exciting thing. This is what high energy physicists, they laugh at us. They say, oh yeah, you do things like that. You figure out how much laser intensity you can put through things before you break them. So, well, this could actually be important. Let me motivate this as we go. Okay, why would we care about optical damage? It's because optical damage often limits efficiency of nonlinear optical processes. Let's say we're interested in second harmonic generation, which we go from omega to 2 omega. And if you plot I out, well, I out at 2 omega as a function of in at omega. You say, hey, that curve is a quadratic. It can go on forever. You can get as much, up to 100%. You can get as much second harmonic as you want, but that ignores the fact that maybe there is some damage threshold. Maybe there is some maximum power that a given material can withstand before you damage the material. There are two primary mechanisms for damage. First one is Avalanche Breakdown, and the other is multi-photon absorption. Now, Avalanche Breakdown is what we're going to talk about next. Multi-photon absorption is what we just talked about. Usually, Avalanche Breakdown dominates. Except for very short pulses. Well, we'll develop a description of multi-photon. We'll develop a model for avalanche breakdown, but it's what does it mean? You have one electron. It gets accelerated by the laser field, picks up more energy, crashes into an atom, releases an additional electron. Now you have two. They get accelerated by the laser field, pick up energy, crash into two more atoms, and eventually you have a huge amount of, a large fraction of the atoms inside your material are ionized. You break chemical bonds, you deposit energy, and the crystal just cracks. Now, I've made this look as if it is something bad to be avoided, but it can also be useful because there is laser machining. and Paul Corkum and Ravi Bhardwaj have been are the local people here working on laser machining. Paul and Ravi started this together years ago. Ravi is now working strongly on laser machining. Paul has sort of backed away to turn his attention to other things. Okay, so you can actually write waveguides into materials, and Eric Mazur at Harvard is one of the experts on this. So you do something like you take fused silica and you focus an intense laser beam on the surface, and you translate the beam across the substrate, or you move the substrate across the beam. Very, very controllable sort of laser damage occurs. Maybe you shouldn't even call it damage. The material becomes more compact. You heat it up, you almost melt it. It becomes a little bit densified. That raises the local refractive index. It becomes a waveguide. And it's really cute to show your visitors. You bring them to your lab. It's one of these Frankenstein things that you write a waveguide into glass right in front of them. 2-photon absorption, that can be useful because you can do 2-photon microscopy. Why would you care about 2-photon? So why would you want a 2-photon microscope when a 1-photon microscope would do? Well, there are two advantages potentially to using 2-photon absorption. Smaller spot size? Well, the laser spot is not really smaller, but if you have a laser beam that looks like this, the 2-photon absorption goes like the square of this. So when you square this distribution, it looks narrower. So you get a slightly, you get a increased resolution numerically, maybe the square root of 2 or thereabouts. That's the first reason. But the second reason is decreased background. And there's a picture in the book that was given to me by Watt Webb. He's at Cornell. And here is the idea. Let's say you take some sort of cuvette and you focus your laser beam into it. And if you have 1-photon induced fluorescence, if you have 1-photon induced fluorescence, let me just see if I have a different color, which might make this nicer. Well, if I were clever, the laser would have been green, and the fluorescence would, fluorescence would be red. But this whole thing lights up. So maybe you're trying to look for something inside of this, but if you're trying to find a bacterium inside of some sort of liquid cell, the whole thing lights up. But if you do it with 2 photon induced fluorescence, you would get something that looks like this. Just at the highly localized in both the transverse direction and the longitudinal direction is the only place where you get appreciable fluorescence. Okay, so you can so this, of course, is also used for laser machining. Because of the highly nonlinear nature of the process, you can write structures that are a bit, well, you can write inside of a material. So, I mean, you can write something into the inside of an optical material by focusing into the inside of it. Okay, so that's what is good and what is bad about optical damage. Actually, let's first before we do the theory, let's take a look at some empirical results. So, some laboratory results. This is a quite well-known study done, 1996. But I guess if somebody does it right, the fact it's 20 years old doesn't make it wrong, just because it was done a long time ago. This was some work by Stewart all PRL 1996. And here's what they did. They measure the threshold fluence for damage. And fluence they measure in units of joules per square centimeter. Okay, so if you're doing short pulse lasers, it's often, you know how much energy you have. You don't always know exactly how much intensity you have because you have to make a very accurate determination of the time evolution of the pulse. So just for practical reasons, you ask how much energy did I have to dump into the sample in order to damage it? And they did this as a function of pulse width, going from, in picoseconds, going from 0.1, 1, 10, 100, and 1,000 picoseconds. And they did it for 2 materials. They did it for fused silica, and they did it for calcium fluoride.
That's 1 micron?
Oh, yeah, what wavelength? 1.06. It might not be fair to say that Thai sapphire hadn't been invented, but it was not in prominent use at that time. And what are the values here? So up here, This is 50 joules per square centimeter, and this is a log scale, so maybe this is 10, and maybe this is 1 joule per square centimeter. This point up here is 50 gigawatts per square centimeter. Well, I have the real plot in the book. So this point here, for 1 nanosecond, 50 joules is an intensity of 50 gigawatts per square centimeter. And down here, this one here was 2 terawatts per square centimeter. So those are numbers just to keep in mind, that damage thresholds can be in the many gigawatt per terawatt range per square centimeter. But look at this trend here, how it changes with pulse width. Now, in both cases here, they go as pulse width to the 1/2 power. And then they level off. This region here is avalanche, and this region here is multi-photon absorption. So they claim. Well, I believe them. They were at Livermore. They said, we took the world's biggest computer, which probably at Livermore they have the world's biggest computer, because you know what they model with it. So they took the world's biggest computer and they cranked away at this, and they convinced themselves that this is avalanche breakdown, this is multi-photon absorption in this region here. So look at what this means. If you care about how much energy a material can take, use as long a pulse as possible. On the other hand, if you care about how much intensity a material can take, use as short a pulse as possible. Those are the takeaway messages here. And this scaling law, we can summarize, is that the fluence at the threshold for damage scales as tau to the 1/2, whereas the intensity at the threshold for damage scales as tau to the -1/2. Okay, so let's now develop a simple model for the avalanche breakdown mechanism. Yes?
If you had a continuous wave laser.
So what I said here, I'm thinking of pulsed lasers. I mean, Stewart didn't go this far, but maybe even up to 10 or 30 nanoseconds, this scaling law still works. Shorter than, longer than a microsecond. It's just heating of the material. which you can do yourself in the laboratory sometime. Take a neutral density filter. Well, not when anybody's looking. Take a neutral, not when the owner of the filter is looking. Take a neutral density filter, put it in front of your laser beam, it'll shatter. Or if you don't want to be that dramatic, you can burn yourself. You burn your finger. Heat up the glass, touch it, and you burn yourself. So it's just heating and then differential expansion leading to cracking is what would happen at under continuous wave. Yeah, thank you for asking that, because who knows? The curve ends at a nanosecond. Okay, so the avalanche breakdown model, as you'll see, this model is a little bit flaky. I think it provides some insight, but when you put numbers in, the numbers aren't quite aligned with, they're not exactly aligned with what people have measured. Let's let n of t equal the number density of free electrons. Let's let W equal the ionization potential of the, well, let's call them molecules. And let's let Q be the kinetic energy of the electron. Let's develop a rate equation model to see how these quantities behave. And let's assume that dN dt is equal to n times dq dt times 1 over W plus recombination and we'll ignore recombination. So we'll assume that the laser pulse is short enough that it can it can ionize atoms, but it's not long enough for the atoms to recombine during the pulse duration. So you maybe your laser is running at a kilohertz, so you send in a short laser pulse, you ionize some fraction of the atoms, and by the time the next laser pulse has arrived, they've all recombined, but no recombination during the duration of the laser pulse itself. So how do we determine the kinetic energy of the electron? Well, this kinetic energy is going to be equal to the force on the electron times the distance through which the force acts. And this distance is 1/2 at squared, and the acceleration will be E over m. So and E is just some measure of the peak electric field strength of the pump laser beam. So you put all of this together and you find that Q is equal to E squared T squared over twice M. T squared, just like half an hour ago. Fermi got rid of this one way. We're going to get rid of this the other way. I said rate equation. So, if you want this to obey a rate equation, you really wanted this to scale linearly with time. So what's going on here? Well, I mean, this is not wrong, because I mean, it's based on some very, very simple physics. But this result holds for t less than tau, where tau is some measure of the mean collision time. We'll assume now these are hard collisions, so that when the electron collides with something else, it will lose a lot of its energy and impart the energy to that material. So and this collision time could be picoseconds or even much shorter than picoseconds. But how do we determine the energy that the electron will acquire over longer time periods, which are the ones we actually probably care about? Well, we can argue that the energy that it will acquire by time t is the energy gained in time tau times the number of such intervals. Well, the energy gained in time tau is just this evaluated at tau. So this is E squared tau squared over 2m. And the number of such integrals is just t over tau. So you multiply, you just multiply these together. Let me get some more room over here. What we cared about was dq dt. So this is just E squared tau over 2m. Okay, so let's come back to our rate equation. Actually, let's look at it a little bit. It says that the time rate of change is proportional to how many are there already. Well, that's because it's an avalanche breakdown. So each free electron is free to become accelerated and collide with an atom and release an additional electron. So now we've convinced ourselves that dq dt is just a constant. So this is just an exponential solution. So we see that n of t is n0 times e to the gt, where g is e squared tau over 2mw. Now, what is n naught? How in the world do we know n naught? N naught is the number of free electrons that are present in the absence of laser excitation. Well, semiconductors can be doped, and doped semiconductors have an electron concentration just by the chemical makeup of the material. Any crystal is almost certain to be imperfect in a way that maybe there are atoms that have the wrong ionization number or valence state to participate in the chemical bonding, and you're going to have free electrons or free holes that are present in the material. So, so we don't know what this is. Now let's make a physical assumption. Assume that damage occurs. If n of t is greater than some threshold for damage. And here t is the laser pulse duration. So if by the end of the pulse, right, our model here says that the number of free electrons keeps growing. If by the end of the laser pulse you have a certain number of free electrons, you're going to damage the material. Well, we don't really know what that is either, but people who do this for a living say that it's something of the order of 10 to the 18th per cubic centimeter. But now let's take this equation here and combine it with this equation here. So this tells us that the threshold for laser damage is E squared at threshold is equal to twice the mass of the electron, the ionization potential over E squared tau t, and the saving grace is that this is the natural logarithm of n threshold divided by n naught. So even if you don't know these very accurately, it only comes in logarithmically. So you take any realistic guess, and you're not going to be off by more than a factor of 10. And so people who do this for a living think that maybe this is about 20 or so. So once the number of free electron grows by e to the 20th, that's when severe damage is going to occur of the order of 20. Now, my best guess at these numbers gave me about 1 gigawatt per centimeter squared. Oh, I guess I could. Well, I just took the mass of the electron. Well, if I take in the reduced mass, I could have driven this up a bit. For W, I took 5 electron volts. For tau, I took 10 to the minus 15 seconds. And for the laser pulse duration, I took 1 nanosecond. So this was the one that for fused silica we said was supposed to be 50 gigawatts, and I calculated 1 gigawatt. You can test me out on this. I see I did the calculation in Gaussian units and then converted. So let's not, let me not show you the details, but beyond that, why would you want to see the details of plugging numbers into a formula? Okay, so that's the end of the damage section. Question?
So in the book, and also the picture that you drew, of the actual measured dependency?
Yes.
Yeah. There's a line drawn through it. Is that the line that's drawn?
That's the one where I labeled it tall to the 1/2?
Yeah. So it must not be.
Well, I've erased it now. Well, let me take a look.
Just wondering what line that is. What function
Oh, So, first, don't blame me. This is reproduced directly from Physical Review letters. Don't forget, people were not as adept at Adobe Illustrator in 1995 as they are today. What they mean is that both of these straight lines are tau to the 1/2. Let's see, this is, how does this work? This is a log-log scale. So a straight line on a log-log plot is a power law. So that's all they mean. Did I answer your question?
I guess my question is actually about the argument that we just made. So everything that we did here is you're just trying to find how many electrons there are and how much
Right.
energy they got under the actual field.
Right.
So I'm not sure exactly where this threshold of damage is coming in. This is theoretical.
I don't either. So a whole bunch of things. One, it's not exactly clear how this model maps onto the experimental results of Stewart. This, well, yeah, I guess it does. I mean, there's a pulse duration here. Let me also say this was meant, it was intended to be a crude argument? No, it was not intended to be a sophisticated argument. I mean, you just ask yourself, what is the simplest mathematical formalism that would capture the essence of what we mean by avalanche breakdown, and this would be it. I think you said, where does the 10 to the 18th come from?
Where does damage come in?
The argument, the conceptual argument is that you have a material, a piece of glass. I will break one chemical bond inside of it. Does the glass shatter? I don't think so. I will break 2 chemical bonds inside of it. Does the glass shatter? There's a certain point after you break a sufficient fraction of the chemical bonds inside the material that it loses its integrity and breaks. Or you dump so much heat into it that it breaks. So there are people who spend large fractions of their lives studying laser damage, and I'm not one of them.
As like a next level to this, don't you have to start adding in things like crystal structures and things like that?
Oh, yeah. Well, yeah, I mean, probably this is so crude that there are other things you want to put in first. Transport properties. Yeah, maybe transport properties. An electron that you make here doesn't stay there. I mean, it moves around. Yeah, I mean, you could drive yourself crazy trying to do this right. If you know Zahir Alam, ask him. I mean, he's not working on laser damage. He is working on the nonlinear optical response of indium tin oxide. and we believe that the mechanism there is very similar to this, except on most days he doesn't destroy his sample because he wants to graduate. So we're getting way off base, except you've heard me talk about this in the public lectures that I gave. So in indium tin oxide, well, in fact, let me tell you the lecture I wanted to give today, except I sat down last night and I couldn't get it done in time because it turned out to be far more subtle than I'd appreciated. Here was the lecture I wanted to give today, and because I was asked, now you've encouraged me to do so. Gold has a nonlinear, has a chi3 value that is 10 to the 6 times larger than that of fused silica. So you ask yourself, why do we use glass and not gold? Well, because light doesn't go through gold is the obvious reason. But then there are tricks you can play. You can get a very thin layer of gold, and you can, so if you want to make the measurement, you can make the measurement. Just take a very thin layer of gold. The other thing you can do is to make a colloidal suspension of gold. So you have gold nanoparticles suspended even in water. And just because you've diluted the gold, you can get a laser beam to pass through that cell. The question then is, why is it that gold has such a large N2 value, or chi3 value? It's a hot electron effect. Well, it's very much like this. So gold is a conductor, right? It's a good conductor. That means that the conduction band is about half full. I mean, if it were empty, there would be no charge carriers there. And if it were entirely full, then for more subtle reasons, well, think about holes. If it's entirely full, it's the holes that conduct, but there are no holes, so that can't work either. So, why does gold have a very large nonlinearity? Let's say that you choose a laser frequency that will go somewhere in the valence band to somewhere in the conduction band. The laser gets absorbed. Right? Gold does absorb. Well, what doesn't get reflected gets absorbed. It heats up the electron. But the electrons have to obey a Fermi-Dirac distribution. So that changes the electron distribution. So let's say that no, I've confused even myself. This is the energy direction. So, and this is the occupancy factor. So, at a temperature of 0 Kelvin, call this the Fermi energy. So at 0 Kelvin, all of the electron states are filled up until the Fermi energy. But now T equals 10 to the 4th Kelvin. Don't trust the 10 to the 4th. You look it up. But this is the electron temperature. Not the lattice temperature. The lattice temperature is what we were talking about before. You can burn yourself by picking up a glass filter because those are the phonon modes that describe what we usually call the temperature of the material. The electrons can have a much, much higher temperature. So the electron distribution at high temperature might look very much more like this. So you have fewer electrons here, you have more electrons here. That entirely changes the absorption spectrum of the material. And then by Kramers-Kronig, that changes the refractive index distribution of the material. So the logic is that the laser heats the electrons. This smears the Fermi distribution. This model has 3 different names. I will tell you all 3 of them. Then you can at least pretend to be knowledgeable. I'm joking, but I'm not joking. If you don't know the name of something, how do you even do a Google search on something if you don't know what to call it? This is called the hot electron model, or it's called the Fermi smearing model. Or it's called the two-temperature model. It's called the two-temperature model because the electron temperature is different from the lattice temperature. And there are different time scales associated with the electron temperature equilibrating with the lattice temperature. It's called the Fermi smearing model because of this, and it's called the hot electron model because that's what leads to Fermi smearing. Okay, so here's the, this is about as far different from nonlinear optics as the two-level atom that we treated. This is a very complicated model, but it's a huge, huge nonlinearity. The laser hits the electron. That changes the Fermi distribution. This changes the absorption and refractive index distribution. So to implement this model, you have to know what is the heat capacity of an electron gas. So I said, if you want to know more, ask Zahir. Zahir has spent the last month calculating the heat capacity of an electron gas. But if I didn't tell you why he spent the last month calculating the heat capacity of an electron gas, you'd have no idea what was going on here. Okay, so professors have this tendency. A student asks a question, you don't know the answer, but you answer a question that you do know the answer to. But what was your question again? It was this model here. It's very, very much related. So this is one model for avalanche breakdown in a material. The process that, well, we believe we do not have avalanching in this process, but who knows? I mean, once you change the electron distribution here, then you've changed how much of the laser gets absorbed by the material. Now, you have to take the course again next year if you want to have the complete lecture about the nonlinear optics of metals. But of course, this is plasmonics. I mean, this is a huge area. It has blossomed since the time that I wrote the third edition of the book. That is one of my primary reasons to write a fourth edition, is that plasmonics has become a very important topic, and very little plasmonics is in the present version of the book. So thanks for asking. Now, are there more questions? I could start a new topic, but I don't want to, and you don't want me to. Should we plan for the final? We haven't talked about the final, have we? We've chosen a time for it. We've chosen a date, right? It's on our... it's coming right up, is it? What did we decide? It's what? I have to write the dumb thing then. Yeah. Look, I know very well that you do your homework the night before it's due. Why don't you think that I write the final exam, maybe the morning in which it's due? Okay, so I'm going to write the final exam. You saw the midterm exam, so you know my style of writing questions. Philosophy. If you ask a student a very difficult question and the student can't answer it, you've learned nothing. So some of the questions have to be easy. Right? Some of the questions have to be easy, because if not, it's highly probabilistic. I love stories. I think you know that. How many of you have taken TOEFL? TOEFL. English, I forget what TOEFL stands for.
Test of English as a foreign language.
TOEFL, Test of English as a Foreign Language. So my European friends tell me, that, not European, Euro languages, like Spanish, that here's, if you're not American, here's how you do well on it. You see, in the old days, tests were just on paper. This is now a computer-based test. So depending on how well you do on the first 5 questions, then they determine what questions to ask you next. So the first questions are standard English words, which foreigners might not know. But all the ones that are cognates of Romance languages or German languages, you know perfectly well. So you walk into the exam, you guess at the first 4. If you guess the right answer, then they will ask you the questions that they think are more difficult, but which you know are easier, because they are cognates of European languages. So it's the avalanche effect, right? It's the avalanche effect all over again. So I'm not going to do that. At least you will all have the same exam. Yeah, we could do that. Computer-based. If you get the first one wrong, then you get an easier one. And they keep getting easier and easier until you finally get one right, and then you can start back up again. No, but that's the whole point. I think that's a really, really bad idea as a way of doing an exam. I like intuition. I like understanding. You've probably heard me say this, most of my exam questions are not heavy on math. I mean, if you have the insight to see what's going on, you think for 5 minutes and you write down the answer. Or you could start with Maxwell's equations and spend 3 hours and get the answer. I mean, anything can be worked out using formal methods. Let's see. It will be a 3-hour exam. Oh, just for fun, the midterm. I forgot to ask Fred. I intended that to be reasonably short. I said you could have 2 hours. Is that what I said? and I told Fred you could have 3 hours.
You said you made a 2-hour exam for 3 hours.
Yeah, that's what I told you? Okay, but I don't even think that most of you probably needed 2 hours to do it. Yeah. Okay, so I said that to take off the pressure. I mean, if you think that you're under time constraints, you might not do as well as you would otherwise. You say you have as much time as you want, then you realize that 45 minutes was really all you wanted to do it. The final might be a little bit harder. No, the final might have a broader range of difficulty on it because I really hate giving failing grades in a course, but you can't give everybody an A either. So you're stuck between these two bounds. I mean, if you make it too easy, then everybody gets the same score, well, you can give everybody an A. Maybe you have no choice but to give everybody an A, but that really defeats the whole intent. We can question whether we even like the concept of grades, but the system still says that we give grades, and if we give grades, I will do my best to make the grades reflect what I think your understanding of the material is. For the top of the class, I will rigorously grade on the basis of your scores. For the bottom half of the class, if I think you understand the material, you're going to pass. And I will be less concerned, I've told you some of this in person, I will be less concerned about how the numerics work out. The University of Ottawa claims that they have an absolute score, right? That if you get 65 or lower, you failed the course. Yep, believe it or not, it's true. No, but I can use a logarithmic algorithm. I can use a logarithmic scale if I want to for the bottom half of the class. So I will do my absolute best not to give failing grades. So it's a sort of a different. That's why I say logarithmic. That you don't want. No, you want to send exactly the right message. I mean, if you think that somebody deserves to pass, but really did not master the material, maybe you don't want that person to take an even more difficult course in photonics. So, I mean, feedback to students is very useful. So, I mean, there are lots of issues involved in knowing how to grade a course. Most students think I give pretty good grades, or at least the ones who get good grades think I get pretty good grades. Okay, any questions about the final?
How much is it worth?
It's whatever I said. I forget.
50%.
50%? Mm-hmm. Oh, let me tell you that story. On the one hand, I will not change my algorithm, but usually a good engineer puts tolerancing on their things. So I always first grade the course the way I said I would. Then I change the grading algorithm plus or minus 10%. And in 30 years of doing this, it's never mattered. No, it made minuscule difference. If I change the algorithm and a student who was here suddenly becomes here, I might think of giving a higher grade. If a student who was here suddenly becomes there, I stick with the announced procedure for grading. There's a concept of some people just had a bad day once. There's a concept that people should be judged by their successes, not their failures. So if you're just playing better at one part of the course than the other, that will really serve you well later in your professional career. But in the end, pretend that I'm just going to grade by the book, because that turns out almost always to be consistent with my intuitive feeling of what the grade should be. With one exception, which I said already. If I think you understand the material, you're not going to get a failing grade, no matter how the numbers work out. Anything more? Okay, so right next to yes.
For the exam, how many sheets?
Oh yeah. Did everybody save their cheat sheet from the first exam? Is there anybody who didn't?
I didn't, but it doesn't matter.
Okay, so you can bring in 2 then. You can bring in the old one and a new one. Am I correct that it almost didn't help?
Not at all.
It almost did not help, right? I mean, people, you don't know Linus and his security blanket?
No.
Yeah, no. The cheat sheet is like a security blanket, right? You would really feel, you'd feel very nervous if you didn't have it with you. But now, it didn't help either. Because and I think the way it helps is to write it. You could write it and throw it away. It's preparing that level of notes that's what's useful, not actually having them with you. So, yeah, bring up to 2 sheets of paper, that's 4 sides, of handwritten notes, your own handwriting. Yeah, I have to write that exam. Homework is due today, right? Last assignment? Okay, so I will deal with that. What do I mean? If those problems turn out to be on the final, I will make sure you get them back in time. And was it not obvious what I meant? No. Okay. So I forget, what was this one? It was the phase shift required for nonlinear processes.
But we have the correction till assignment 5, maybe 6.
Correction?
Like we received the solution up to assignment 5.
Okay, so I'll deal with that. I'll deal with that. Some people just need to be reminded. No, I'm not going to say bad things. Some people need to be reminded more than other people need to be reminded. Oh, the homework that was due today, wasn't that interesting? That everything in the life you've ever wanted to do in nonlinear optics requires pi radians of phase shift. Right. That was the takeaway message, is that think in terms of nonlinear phase shift. I mean, this is the dimensionless parameter that tells you when you have strong nonlinear optical interactions. Yeah, and one of you pointed out to me that 1B had been misworded. You got the corrections. And you understood? I mean, it was clear to me what I meant. No, but as a technicality, I mean, what I put on paper didn't make any sense, right? Because you don't have a Rayleigh range if you're in an optical fiber, for example. But you have what the Rayleigh range would have been had you not been in a fiber. And then the second part of it, what was that? Put in numbers, was it?
Gaussian.
Oh yeah, here's the largest nonlinearity ever measured before Zahir, but I didn't want to rewrite it. And can you do single photon switching? Was that the question? What was the question? It was
Minimum power.
well, yeah. So, am I correct that the minimum power was more than 1 photon in a picosecond? Yeah. So I mean that's where the problem was heading. I mean that's sort of the goal. Well, one of the many goals of nonlinear optics is to do a single photon in the control field. A single photon controls another field. The world has done that now, not in traditional nonlinear optics, but in cold atoms. No, I believe that in cold atoms you can have a single photon field turning on or turning off another field. But that's very different from, well, it's maybe so important that you would make a device that way. But I mean, people call MOTs on the chip. MOT, magneto-optic trap. So people have done this. You can build a magneto-optic trap on a substrate. But boy, that's a hard way to get ahead in life. More questions? Let me see if I had anything. Okay. We move on then to the discussion, right? Well, which we've been doing. But we said that it would be nice if the last part of the class had some discussion. Let me see if I have some notes. You can think too while I'm thinking. I'm trying to think of interesting questions to ask you. You can think of interesting questions to ask me. So where did I put these? I had a whole list of discussion topics.
I have a question.
Good.
General question about nonlinear optics.
Okay.
It is related with some structures, call it like quantum dots, quantum wells, quantum wires.
Now you have my attention. I found what I was looking for. Okay, now let's start over.
Okay, sure. I have a question of general nonlinear optics, and it is related with these things, call it artificial atoms.
Yes.
Like quantum dots or something.
Right. Yeah.
So, and I have heard that the nonlinear optical properties of those objects are large.
Yes, I think so.
But my question is, and the reason.
But of course, they're large for an atom, but they're not large for 10 to the 23rd atoms. So, but keep going.
Yes. Yes. So they claim that they are large because they can tune the energy levels.
Yeah.
So well, you can make them large. So my question is, when we have these structures in the lab, for example, we can think on them like being really one artificial atom, or should we think them about like a bunch of atoms that have an overall effect?
Oh. It's funny that my answer was the answer to the question that you asked later. It violates causality. Yeah. Well, I think when they call it an artificial atom, you're to think of it as if it's a single atom. I mean, so a collection of a quantum dot is an artificial atom in a certain sense, and the quantum dot has like 10 to the 9th or more atoms in it, but it behaves like a single atom. Now, what I've not looked into myself are some rules. Did we do some rules this year in the homework? Refractive index of the two-level atom? Okay. So there's something called the sum rule. The oscillator, see, oscillator strength sum rule.
Oh,
Yeah. So the oscillator strength sum rule is you for every optical transition in an atom, you assign an oscillator strength, and they have to add up to 1. In some of these artificial atoms, I believe that it can add up to more than 1, because there are more than one. There's more than one atom there. So in some of these solid state structures, in some ways it's obvious that it could add up to more than 1, but it really does. I mean, you have things that look like energy levels, and you calculate the absorption coefficient associated with one of these, assign an oscillator strength to it, and you get an oscillator strength larger than 1, I think. I think that's true. And if so, that tells you why artificial atoms are important, that they actually can interact with the light more strongly than a real atom could interact with the light. So how far can you be from a mountain and see the peak of the mountain? No, I'm curious, what answers did you get? How many think it is less than 10 kilometers? Good. How many think more than 10 kilometers? How many think it's less than 200 kilometers? Yeah. So I mean, I think my answer is 100 kilometers. I mean, there's no right or wrong answer. There's no right or wrong answer. And it depends on how good your eyes are. You say, oh yeah, I can see a 1% effect. Mountains look blue in the distance because the light that comes from the mountain gets scattered along the way, and the blue gets scattered more. So it depends on how you think about the question, but it's about 100 kilometers. That next time you're in the Laurentians, you can keep that in mind, that you learn something useful. The sodium atom. The ground state is 3s. The first excited state is 3p. This is j equals 1/2. This is j equals 1/2. This is j equals 3/2. I hope you agree. That was what the homework was. But now if you measure the absorption as a function of frequency, you're going to get one peak and a second peak. And what is the ratio? I guess if they don't have the same width, it would be the integrated area. But let me draw them with the same width, because if they were Doppler broadened, they would be. Okay, so what is the ratio of the peak heights?
Degeneracy ratio.
Okay, so, but what is the answer? Wait, that was the homework problem, wasn't it? 2 to 1? So how many got 2 to 1? Yeah, okay, it's 2 to 1. Yeah, it's almost disturbing. No, that it's just 2j plus 1. But so you think for about 3 hours, and then you say, oh, it's just 2j plus 1. Yeah, so it is just the ratio of the degeneracies. You can believe that, and then you're done. But it's at one point in my life, I was very glad that I worked my way through all of this with all the magnetic sublevels, all the Clebsch-Gordan coefficients and everything. But it is just 2 to 1. What other things? How many people were able to calculate the town's profile? And how did you do it? I've never done it myself.
Oh, it was pretty tricky.
Oh, that I can believe, yes. So did you use Mathematica?
I did get Mathematica to figure it out, yeah.
Mm-hmm.
The trick is the boundary condition.
Mm-hmm.
Making it vanish at infinity is quite tricky.
Making?
Making it vanish at infinity.
Oh, yeah.
That boundary condition.
Yeah.
There's no natural way to do that.
Okay.
So you have to come up with a method to find
Ooh.
the equivalent initial condition.
Yeah. Oh, yeah. I see. Yeah. It doesn't, because Mathematica doesn't know that lasers have a finite energy. so it can find solutions that don't vanish at infinity. Okay, so, yeah. Did you use split-step Fourier methods, or how did you actually set up the problem?
Well, I used the built-in DE solve, so I don't know what it's using. I
Okay.
don't remember what it was using inside. And then it diverges to plus infinity or it diverges to minus infinity, depending on what initial condition you set.
Okay,
So you just iteratively find the initial condition that makes it not diverge at infinity.
okay.
I had to renormalize
Mhm.
every iteration because it just tends to lower down.
Because it die away,
It
or?
dies away.
Mhm,
in
okay.
my-
So you just boosted it
You
up?
just boost it up every
Mhm.
time. And
You did it the same way?
No, I use Newton's method.
Yeah.
On the finite element.
Okay.
I'm sorry, I learned the terms in French and
Yeah.
I'm trying to translate
Yeah, yeah.
as we go. But just
It sounds right, finite element method?
And
Okay.
you have to exclude a singularity at the origin if you use the Mathematica built-in method.
Okay. In my own mind, it was not clear to me that Mathematica was the right tool to do that one problem. It probably isn't. Mhm.
I use math.
Okay. Okay. I assume that no one found an analytic solution? It's believed that there is none, but it could be worth looking at. Just an insight. Yes.
This is probably, well, might be a simple question. It's a question about phase matching, and it's sort of related to what we did in the lab.
Mhm.
So say you have a crystal and you're generating second harmonic,
Mhm.
and you tilt the crystal, and obviously that affects the phase matching.
Right.
That affects your harmonic yield.
Right.
So I'm looking at the problem and I'm trying to understand how the physical tilt of the crystal actually affects the phase matching method. Because I want to relate the
Oh,
tilt
yeah.
maybe back to the tilt angle,
Right.
back to the phase difference.
The length of the crystal.
It's the refractive index. Which shows you that
Well,
affects length and not the actual weight.
You want to know conceptually, or you want to know the best numerical technique?
Conceptually.
Okay. Well, conceptually, as you rotate the crystal, you change the extraordinary refractive index. The ordinary and the extraordinary. The ordinary does not change with angle. That's why it's called ordinary. But the orthogonal polarization changes depending upon the orientation of the crystal. And in the book, there's a very simple example that's worked out. And maybe you were not in class that day, because we worked it out on the board here.
Might just not remember. But
Yeah.
I think it's
Yeah.
thanks.
Okay, so I mean, that's the conceptual point. Let me give you something to think about. I mean, everyone. Okay, I mean, this is the problem here, which is relatively straightforward. Now, here is this is chi 2. Now, there's another process that naively looks to be just the inverse of this. But here you come in with a pump laser and you generate a signal and an idler photon. But the point is that here, all of your initial conditions are prescribed. Here, nature, there's a few too many things that nature can do. It can, well, this, the signal field can come out with any energy, well, essentially any energy, as long as omega signal and omega idler add up. And it can come out in any angle. So there's a huge number of possibilities for what can go on in parametric down conversion. And that makes it intriguing, makes it fun. I still don't have a crisp answer. So when you ask me, how do you do phase matching for second harmonic generations? Well, here's how it works. If you ask it for this process here, my answer is that every special case you work out separately. I don't have a big picture for what the possibilities are, or what the constraints on the possibilities are. Oh, a report. Earlier in the semester, there was a homework problem that said we replaced del dot E. We set del dot E equal to 0, even though there was no fundamental justification for doing so. But please calculate and see whether whether there's any appreciable error in setting del dot E equal to 0. My friend John Sipe from University of Toronto, I told him about this. I mean, we share ideas for how to teach. He said, well, why don't you just formulate nonlinear optics in terms of the D vector, not the E vector? I mean, at that point, your life would be so much easier. And I said, hey, that's a good idea. In fact, maybe you don't even have to redefine the susceptibilities. Maybe it's only once you get to the wave equation. Just solve the wave equation for D instead of solving it for E. And all of many of the difficulties then disappear. And once you're back in free space, knowing D, you can easily determine what E is. Okay, so that's a follow-up on one of the homework problems that you did. Am I correct? So did anybody find cases where an appreciable error occurred from by setting del dot E equal to 0? You didn't, right? I mean, I ask you to show that there was none, but deep down inside, if you found one, that would be that could be very interesting as well. Did we talk about the slowly varying amplitude approximation? I think that one can easily break down. I'm not sure if I mentioned that, but those of you who work with short laser pulses. In fact, it was Thomas Brabeck, who was one of the first people to do this, to develop a theory of how ultra-short pulses, I mean several cycle pulses, propagate in a nonlinear material. So the slowly varying amplitude does not work there. You have to work with the field itself. Were there any other? Okay, your turn again. More questions? I could see somebody thinking about asking one.
Well, if no one's asking a question, I would love to hear a professional answer of a simple question, what is the refractive index?
Okay.
I'd love to hear a better answer than what you hear in my introductory. I want to hear the whole story.
Okay, so,
Don't make the question.
well, it's called the refractive index because it determines how refraction works. So if you have air and you have N and you have a ray of light coming in, it will bend toward the normal. So this is, let's call this theta, let's call this N1, and call this N2, and call this theta 1, and call this theta 2. And then, I don't think I'm telling you something you don't know already. Then N1 theta, sine theta 1 is equal to N2 sine theta 2. And I think we should not lose sight that that's what you mean by the refractive index. That's why it's called the refractive index. So that's the first level of answer. Now, we've talked about this a couple of times in the semester. So what is the conceptual origin of the refractive index? Was that your question? What is the physically, where does the refractive index come from?
Sure, let's answer that one.
Okay, I already said, I can only answer the questions that I know the answer to. So I will take what you said and, no, I've said this already during just a couple of weeks ago. But let me remind you of this. And at least in the book of Born and Wolf, this is called the Avold-Oseen extinction theorem. It's actually even more interesting in terms of absorption. So where does absorption come from? So here you have, let's say, a thin slab of material, and here you have a thin enough that you don't have a lot of absorption or anything. So now let's call this E1, and then all of the dipoles in here radiate a field, and let's call the radiated field E2. And then the total field here is equal to E1 plus E2. And let's not put in the e to the ikz yet. We know how to put that in. So it's the interference between this and this. So if you have, let's do the complex plane, and let's say that E1 lies along the positive direction, and let's say that E2 is in this direction here, then you get attenuation. I will distinguish, at least semantically, between attenuation and absorption. Well, those of us who believe in energy conservation, they're probably equal to one another. But by attenuation, I mean that the field in the forward direction becomes less strong. So here is how you can understand it in terms of a very physical picture. These atoms emit a field that interferes destructively with the incident field already. So this would be the imaginary part of the refractive index. But if you have something like this, and the if this is E1 and this is E2, then this will be total, and this gives rise to the real part of the refractive index. And I said this is given in Born and Wolf, but I really like the one in Sargent, Scully, and Lamb. Laser Physics. Very, very nice book. This is not what the book is about at all. But at the end, Appendix A says, you know, I've always wondered what the origin of the refractive index is. Let me just tell you this here. The book is very strong on Lamb's theory of the laser, which Lamb loved Clebsch-Gordon coefficients. So it was about gas lasers, helium neon lasers, argon lasers. I said, well, how do you understand the laser works if you don't keep track of what each magnetic sublevel is doing? I mean, equation, just page after page of messy formulas. But that's only like 2 or 3 chapters of the book. So the rest of the book is an introduction to quantum optics. And it's where I learned a lot of these things. So, I mean, of course, Murray Sargent did all the work, right? He was the postdoc. He was the professor. He was the Nobel Prize winner. But at least they allowed him to put his name first on this book. So people don't know that book. Yeah, it's worth checking out. Yes.
Just trying to understand what you just showed there. Maybe a good question for me to ask in order to get a better understanding is what would happen to the real and imaginary part if you, say, double the density of the medium?
Ah, sure. So, yeah, so if you double the density of the medium, I guess, then E2 would look like this, and you'd have more attenuation. And in this case here, you double this. So of course this is the phase angle. So I mean, this describes a phase shift.
You just change the number of electrons inside this thing?
Well, yeah, but in most we usually think that each atom produces one electron, or at least one electron per atom strongly contributes to the optical properties. So I took you to mean that when you change, when you double the density, you double the number of electrons that can wiggle in response to the laser field.
So it goes more towards the attenuation. So
Right.
higher imaginary or less.
Right. Now, of course, we can get the right answer much more easily than doing this. So if you want the so if you say how does this depend on number density, we know the answer. But in terms of these pictures, I think they're very useful in terms of understanding what's going on. And there are tricks people play. No, this picture can be very useful in terms of you turn this on, you turn this off. If you turn this off suddenly, maybe you still get this wave that's the emission from the atoms inside of this. And you say, oh yeah, those are precursors and all that. So this model has some richness to it. It would not be a precursor, that would come later, I guess.
So the effect is that you have, say, in that picture, you have those three atoms that are, have three dipoles there.
It's actually more like 10 to the 23rd, but anyway.
But if you right now, they're just picture them frozen, so that there's some distance away. You come in with a light of some wavelength. So your destructive interference conditions are set already by whatever distance you look at it. Now you just have to squeeze these things together. Right now, that's the thing that's changing, is the actual interference effect. So when you calculate the phase shift, the phase shift is effectively the phase shift. Refractive index is effectively the phase shift.
Because we're talking the exact forward direction, plane waves. So the nature of the interference doesn't change. It's just that the generated field is stronger. So the effect will be larger. You're not with me.
There's more constructive interference between the two fields and
Just make it clear. These atoms are not talking to each other. Each of these is emitting a dipole pattern. You go far enough away that you get complete if you want, E3 plus E4. Okay, so each atom generates a field. That field interferes with the incident field, which is E1. And you can understand both the imaginary part of N and the real part of N in terms of this re-radiation picture. So I meant nothing more, nothing less than this. And we're relying on a book I read when I was your age. So now I thought about it in the meantime, but they worked out the details there. Even the eye. Anybody who's known the Fresnel diffraction integral? This eye. Yeah. So if it's the real part of the refractive index, you see that the radiated field is phase shifted by 90 degrees with respect to the field that drives it. That drives it. So when you, that's why it's such a fun calculation. You derive the square root of -1. But I always wondered where that comes from. You see the Fresnel integral, and they put it there, and sometimes in a very formal derivation just comes out. But if you do this, it's called a dipole sheet. You have a sheet of dipoles and just see how it interferes in the forward direction. Maybe that's enough for one day. It's 5:30. I have my obligation to teach you until 5:30. Okay, so see you next week.